to Doz's Television Kitchen. Anyway, I know what you're thinking. Doz in the kitchen, he's going to do something silly with a microwave oven. Put a camera in it. It's all been done before. It's passé. We're here because of the humble hob. Now, this is an induction hob, and it's a couple of years old. It developed a fault. One half wouldn't work. The other half worked fine. Mrs. wasn't very happy. So we took it apart, worked out how it worked, effected a repair. It was an optocouple. Sorted. Didn't have to replace the main board, which was going to be expensive. Replaced a quid's worth of optocoupler. Brilliant. How does the induction hob work? It's amazing. Underneath each ring, not really rings, they're just gaps really. Underneath each one is a coil of wire. And that coil of wire is fed with a signal from our control board. It's about 30 kilohertz, and it switches with a bank of IGBT, or insulated gate bipolar transistors. They're like an ordinary transistor, NPN, but they have sort of half a FET on the back, so the gate is insulated with very, very high impedance from the emitter and the collector. So you have a gate, an emitter and a collector. Brilliant things. Nothing wrong with those. It was an optocouple in the control circuit. Anyway, that is used to switch some rectified mains. Incidentally, the mains isn't smoothed because we want to pull a lot of current. So the mains is just rectified. So it's just lumps of DC occurring. The IGBT switch at about 30 kilohertz and dump that into the coil. Now the coil forms a primary of a transformer, and the secondary, normally coupled with an ion core, is where we pick up our power in a normal power supply. Not in the case of the induction hob. There's no ion core. There's just an air gap, and it's not very much. The coil of wire sits right underneath this sheet of glass, so it's only a couple of millimetres away. But the secondary is formed by our saucepan. Amazing. So primary, the energy is going into the primary, it's creating a magnetic field, and that is inducing a current to flow in our saucepan. And this is why you have to be particular on your induction hob about what sort of saucepans you have. You have to have induction hob friendly saucepans. And here's the reason why. You can't use ceramic, you can't use glass, because they're insulators. No current's going to flow. You can't use copper, and you can't use aluminium. Why not? They're great conductors. The reason is the resistance is too low. You'll put a short circuit on our transformer, and we'll be dropping almost no volts across our saucepan. Therefore it won't be dissipating any heat, and it won't be getting warm. What you want is something in between. You've got a steel saucepan. It's got a bit of resistance. Not much. I can't measure the resistance of that saucepan, but it's got enough. The energy goes into the coils, goes in across our air gap as a magnetic field, and induces a current to flow in the base of our saucepan. The saucepan's got resistance, current, resistance, voltage, heat, power. This saucepan gets warm. Brilliant. Absolutely brilliant. And there's no heat there, so we can just put a piece of something, a piece of paper or whatever, and it won't scorch, it won't burn. Keeps it nice and clean. Wipes out. Very important. There we go. It warms up. So anyway, this got me thinking, well, perhaps if there's a voltage drop across our saucepan, we can measure it. And I've tried it, and we can. And I'm going to show you. Right. This here is my trusty Philips 123 industrial scope meter. It's got two lines missing on the display, two columns, and that's because it's been dropped. In fact, it got dropped quite a long way, but there we go. So please excuse the fact that the display has got a couple of lines missing on it. But let's have a look. Right, so first things first, we want to connect our scope to our saucepan. Never done this sort of thing before, I suppose. There we go. We'll put one end on there, shall we, and the other end on there. Right, there we go. So we've now got an electrical connection across our saucepan. Let's switch on. Right, here we go. It's a nice close-up of the scope. I'll switch the hob on. And turn the power up to full. And we should see, when it comes on, a bit of a waveform. There we go. 27.8 kilohertz. It's a funny shape waveform, but there it is. If we actually slow the time bases down, remember I said the waveform was modulated by raw mains. There it is. There we can see an AM waveform. It's because we're only half wave rectifying our mains. But there we go. It's not a very big waveform, is it? In fact, it's below what the scope will measure on the top left there. If we can get a peak to peak. Measure on A, volts AC. There we go, 52.1 millivolts. And my water's boiling. Brilliant. So there you have it. That's how it all works. The magic of the induction hob. Right. Being as that water's boiled, waste not, want not, might as well make some tea. Thanks for watching.